I correct? Wednesday and Friday in garage, is that right? Well, so on Monday, we'll figure out when the next quiz is. I'd like to get some more, but the next thing we're gonna do is probability density functions of two variables, and then we have to do something with conditional probability that, in my opinion, makes conditional probability a lot easier to understand. So we're going to cover some of that today. And it's almost time, isn't it? Take a look. All right, so questions. Questions about any of the homework up to the last 2 or 3 homeworks. We did section, in the book Cooper and McGillum, 2.5, 2.6, or 2-5, 2-6, 2-7, 2-8 are the sort of the, that's the total span of what we covered. The next, basically, everything's based on the prior information. Any questions at all? I've got problems I'm going to do. Did you have a question?
About the homework?
Yeah.
Problem 7.2. I think it was the variable.
7, probably in the back, section 7.2.
2-7.2.
My reading. All right. All these sections, section 2.6 leads into section 2.7 and so forth, 2.8. We're going to do problems in 2.8 and 2.9, and more or less finish this chapter and then get into 3.
A continuous valued random voltage ranging between -20 volts and +20 volts.
Hold on for 1 second. So we got -20 and +20 is the range, and it's uniformly distributed.
It says continuous value random ranging between.
I think it's uniform, right? Yeah, so this means, if you look at this, the area, if this is the f of v right here, right, this has to be, the total span here is 40, so this has to be 140. Do you agree, class? As far as, because we know the area under the curve of the probability density function over the span of values has to be 1. Go ahead.
It needs to be quantized so it can be represented by a binary sequence. And the first, if the RMS quantizing area is to be less than 1% of the max value of the voltage.
So that's 0.01. Go ahead. You all agree with that first, but it's the max value of the voltage. And the max value of the voltage here is 20 volts, right? Correct, class? How many tried this one? All right, it's a very interesting problem because he didn't say, he says with the standard deviation is 1% of the max. The max is 20, the span is 40. Do you agree with this, everyone? All right, so this is going to be what? That's 0.2, correct? Is sigma v, and that means sigma v squared is going to be really 2 times 10 to the -1 squared, or it's 4 times 10 to the -2, or 0.04. I'm just going to put that down there. And if the units would be v volts squared. Go ahead.
Find the minimum number of quantizing levels.
Okay, so this goes back to when we proved if you have a uniform distribution and you're looking for the actual variance of that, it came down to sigma of v squared, if you have quantizing errors, was 1/12, and then it's going to be the total. Here it's going to be the span of voltage, which is 40. That's the total span of the possible values of voltage. From -20 to +20 is going to be 40, and it's going to be over n, and that's squared. Now we have sigma v squared, and we need n, so this is just going to be arranging things, rearranging things. Do you all agree with this, by the way? If I look at this, I can say that n squared, I can take square root too, but I can say that n squared here is going to be equal to, if I take multiply by n squared, it's going to be 1/12, and then it's sigma v squared right here. divided into 40 squared. I'm just putting it down, and then I'm gonna take the square root of both sides. Y'all with me, class? So, really what I'm after is n, so I just take the square root of this. And that should be, unless I did it wrong, 40 over n times sigma v, sorry, it's 40 over 12, my bad, over square root of 12, right, times sigma v. And what do you get for that? I mean, just get a calculator.
I mean, it's 57.7, so 58.
Yeah, you can't, that's right, 57.7. You can't have 0.7 when the level has to be an integer, so you round it up to 58. Is that the right method? In the solutions, Ryan?
Yes.
I found errors in the solutions in some of them I'm going to mention. To be frank about it, graduate students usually do the solutions, and at times they're distracted. So anyway, everybody get this? What's the next?
I couldn't get access to the solutions manual. I was wondering if you could possibly email that to me.
Has everybody got the solutions?
Yeah. I tried to download it. Like,
Hold on. This is a PDF, right? Do you have a Mac or what do you have?
I have a Windows computer. I tried to download it from the OneNote, and like the download, it just like wouldn't download off the OneNote.
Anybody else have that problem? Can I send it to you after class? Remind me though. Don't let me forget. Okay. I can do that during the quiz. Just remind me before the quiz. All right, 58. What's the next part?
If the number of levels is to be a power of 2, find the minimum number.
Okay, class, this is something kind of important because all the time when you're dealing with analog to digital, anything like that, you're going to have 2 to the n as far as the number of, you could say, of quantized states. So this is 58. Now, if you think about 32, right? If you take 2 to the 4th, 16, 2 to the 5th, 32, 2 to the 6th, 64. 64 should be the next level. So that means the actual, it would be 2 to the 6th, or 64 levels for n. And do they want the quantization error? What do they want?
It just says the number of quantizing levels.
Is that right? 64? Okay, what else?
How many binary digits are required to represent each?
Now, everybody's had basic analog to digital, right? I mean, y'all have had binary math, right? So you can see if it's 64, it's 2 to the 6, 6 levels. Y'all with me, class? It's basically, you're going to have 6 digits. And now, I wish I was, do you remember, what do you call that thing? It's called an equalizer online. It's a digital equalizer. If you've ever seen that, you can adjust basically the frequency, more or less emphasis. You can either decrease or, but that thing takes analog signal. Typically, they do it this way. The highest frequency that your ears can really hear, unless you're a dog or something, is about 20,000 hertz. Mine doesn't go that high because I've been around rifles and I'm older. But what they'll have, if you're going to do this correctly, and just think about this, you have to sample at twice the highest frequency of interest. If you have an audio signal and you want to reproduce it, that automatically puts it at 40,000 hertz is the sampling frequency, minimum, if you want complete reproduction of the audio sound. Then you, as far as quantization, they have the total range of possible, when you take a look at a signal, you're going to have the total range of values from minus to plus, be 2 times the magnitude of V, is the upper limit, and they're going to quantize that, and it's typically 10 to 12 bit quantization, or they're going to have 12 levels. By the way, what is 2 to the 12? Is that 2048?
It's 4096.
What is it?
4096.
449.6. So that would be how many levels for good quantization you'd get. And then the quantization error, if you actually check that, goes way down. And you've listened to digital music all your, probably. Has anybody listened to LP, long playing records, the actual, all right, what do you hear? That hiss is so many more dB above the quantization error noise. you can't even detect the quantization error noise. You'll detect the amplifier hiss if you turn it way up. You'll, even without any signal here, it's sometimes 60 hertz. Do y'all know what I'm talking about here or not? Just keep in mind the levels that you need, the number of bits, then that's 1 zeros that you need to do is significant. And because you're going to be doing that at 40,000 times a second, think of the amount of data. So that's going to be 40,000 times say 10 or 12 bits, right? That's an enormous amount of data just by itself, binary data. I promise you it is. It's amazing how they can do this. All right, what else?
That was all for.
And if we asked, which I might ask, not today, but I shouldn't say that, I might ask, well, what is the actual RMS error with 64 levels? And how would you get that, class? Y'all should know this. Quiz coming up. Well, what would you do? Remember this? Sigma of what? Well, of anything squared, right? Is equal to 1/12 the total span in voltage divided by N, right, squared. You all with me on this? I just want to see what it is. Now before, the level was 0.2, right? I mean, this is, so we have to take the square root of this. So therefore, the new one, when 64 bits, is going to be 1 over the square root of 12. Can somebody help me out here? And here we're going to have 40 over 64. What's the new level? I can't tell you. Oh, this right here is going to be 0.2, by the way. I mean, sorry. I want to know what that is, I should say. What is it?
0.18.
All right, so it went from 0.2 to 0.18, not much of a drop. It's 0.02, the value, and percentage-wise, I'm not sure, but it, you know, obviously, the more levels, the lower the RMS error, as far as quantization error. All right, next. Any other ones you got for me?
2-8.2.
Okay. I may have had that in my problems to do. 2-8.2. This should be a good Friday, by the way. I mean, a great Friday because there's no rain, as far as I can see. 2-8.2. So go ahead. Who asked?
For the random variable x of problem 271, that was the x equals cosine of theta.
All right, hold on for a second. So we got x equals cosine of theta, and we have f of theta, I think I remember this one, from 0 to 2 pi, right?
Yes.
And the height of this is going to be 1 over 2 pi. And we knew that f of x for this one is 1 over pi times 1 over the square root of 1 minus x squared. I kind of remember this one because we did it at least once. We talked about it once, right? Okay, go ahead.
Find the conditional probability density function f of x given m, where m is the event 0 to theta to pi over 2.
All right, so they're saying that the angle is from 0 less than pi over 2, right? Isn't that right? And they want the conditional probability of f of x, right?
Yes.
Isn't that right? So you can do it a couple ways. I don't know how the solutions manual. I think the solution manual does it in theta, but I don't. They use the actual theta type of thing. But if you look at this, by definition, the conditional probability f of x given m is an event that we're saying happens. That's equal to just f of x. Now that's the original distribution. And then do you divide by the area involved in event m? If event m, I mean under the probability density curve. Y'all with me on this? So then you divide it by, and this would be the area involved, and says it is from, it's greater than 0,
Yes.
less than 1. Okay, so from 0 to 1, and this would be simply f of x dx. So if you look at this, f of x is 1 over pi square root of 1 minus x squared, and it's just, I can argue this one. The span of x, if its cosine, is from -1 to 1. Do you all, first of all, agree with that? I mean, based on what they say, because you got a full cycle, theta goes from 0 to 2 pi, which is an entire cycle of the cosine, right? So the span of x, if we take a look at x, can be greater than -1, less than 1. Now, can everybody see this as an even function? People, I'm not gonna ask this, make sure, can you all see this? If it is an even function, the area from 0 to 1 is the same as the area from -1 to 0 in terms of the integral of f of x over that range. How many understand that? Are you with me? Do you understand that? Okay, I gotta make sure that. All right, if you know that, this automatically, without doing it, is gonna be a half. Do y'all agree with that? I mean, this right here. Do y'all follow me? That integration has to be 1/2. If it went from -1 to 1, it would be 1. Y'all with me? So event m happened. If you divide that by 2, it's really multiplying this by 2. And this would be the conditional probability. Now for this range, x has to be greater than 0, less than 1. What else? Is that the right answer? I don't know. Do you have? I'm pretty sure it is. And I think,
Yeah, that's the right.
oh, here, okay. Y'all with me on this one? I'm trying to just make sense of the way we do it. Conditional probability is very important to understand. Remember, anytime you talk about conditional probability, what you're really doing is taking the original density function and you're normalizing it so the area under that curve will be 1. That's the bottom line. Y'all with me on this class? All right, now, is there another part?
I think it's follow the mean.
Yeah, that conditional mean.
All right, now, there's a lot of, these are things you can do. We can do it the standard brute force, right? Remember, that's the density function, right? And it's only valid from 0 to 1. So if we want the expected value of x, given that m occurred, now this is the key. M has happened, so it limits, first we have to use that density function, and our integration goes from 0 to 1, not from -1. So here, it's just going to be this. It's the integral of 2x over pi, the square root of 1 minus x squared dx from 0 to 1. First, do y'all agree that's correct? And I'm going to tell you, you can do this a couple different ways. First of all, without spending a huge amount of time thinking about this too long, your calculator should do this. If you have calculators and do integrations, and I think every single one does. How many do have a calculator that they can plug an integration into? Do you understand how to do that? Or do you understand on yours or not? Behind. No? What kind of calculator? Anybody with an 84?
Me.
Do you have one too, Anna? Just show him, go ahead and do that. But I want to make sure, now I'm going to show you old-fashioned way. If you take a look at this right here, you'll know, I'm just going to make better yet, I'll do it this way. I'll make u squared equal to 1 minus x squared. This will be clear. So what I've done is, I've looked at this based on the fact that I've had calculus about 50 years ago or something. If I look at this, I know the trick is always in that square root off. So I take a look at this, and that means du, right? Du itself is going to be 2u du is going to be minus 2x, and this would be dx, and really u here is going to be the square root of 1 minus x squared, keeping that in mind. If you do this, this integral becomes, I'll take the 2 out of over pi out in front, and I have an integral. X dx is really going to be equal to 2x dx is going to be, put that inside, minus 2x dx is going to be 2u du, so put a minus sign there, and I have u du, and then I have the square root of u squared. I'll get out of your way in a second. Now, the only thing I've done here is I substituted it, you'll notice there's a minus sign there. The only thing I've done is substituted in u squared is 1 minus x squared, and du, 2u du is equal to minus 2x dx into that original expression. But the beautiful thing is what? If you look at the limits of this first, is that, well, if x goes to 0, the u value there goes to 1, right? And if x goes to 1, the u value goes to 0. Do you all follow me on this, class? So now I'm going to just do something that I think everybody gets. First, does everybody agree with this? Now, the square root of u squared is u. U divided by u is 1. So I integrate du here, and I simply get u from 0 to 1, but there's a minus sign, so I get 1 over pi times 1, and that should be the expected value. Is that right? Anybody? You got the solution.
Says it's 2 over.
Good. You know what? That's the reason. I forgot that too. Or did I? Hold on. 2 over pi.
Why is it not 0 since it's an odd function?
Because you're not integrating over the range from minus a to a. It's only from 0 to a. Follow me? If it would have to be symmetric. Can somebody do me a favor with your calculators? Can you simply do this integral for me? I'm pretty sure that that is, wait a second, I forgot the 2. Never mind. There should be a 2 here. Is it 2 over pi?
Yes.
I'm sorry, I forgot the 2. You're right. Okay, so that's the value. What else? No.
That's it.
Let me ask you this, just a question. Now, obviously I did this just by using a substitute. What if I asked for the mean squared value or the variance, either one? Say mean squared value, what would you change here? All right, if it was the mean squared value, right here, expected value of x squared given m, the only thing you would do is this. All right, now, think about what I just did. I said that u squared is 1 minus x squared, right? Square root of that is going to make this u, right? Up here, what are you going to get? X squared there is going to be 1 minus u squared. Y'all follow me on this one? So you're going to have to do 2 portions of the integration, but they're trivial integrations with that substitution. You follow me on this as far as the logic? Now your calculators, I am certain if you know how to use them, can do these kind of things very quickly. If you know how to do them. Now, I mean, if you don't, if you haven't played around with that, you can spend a lot of time. But these are meant to be trivial, not trivial, but not that difficult of integrations where you have to spend a lot of time. Any other questions? I hope do y'all follow the points I'm making here? And by the way, if we did have x, the expected value of x squared given m, then what would the variance be? Let's assume I have the mean and have the mean squared value. How do you get the variance?
Mean squared minus the mean.
Squared, right? You have to take the mean value and square it, subtract it from the actual mean squared value. With me? Conditional probability changes, obviously, the mean and the mean squared value. So you've got to be a little more careful about this, okay? All right, now that said, any other questions? I got things I want to do. So, the first one, this is something I could almost see in one of the microelectronics classes being asked. But if you look at this, this is not a problem in the back. It's exercise 2-9.1. I'm going to hop around on a few of these because these are good in terms of what they showcase, how to apply this. show you another trick on this one. So you have that book. If you look at exercise 2-9.1, this is an exercise. And this is what the last section is an application of all the previous theory to actually real world problems that have significance. And for this one, they give you this. They have a current I, and it's equal to I naught, and then this is going to be forward bias diode. And I'm going to draw the circuit. So basically, if you wanted a circuit for this, think of a voltage here plus the minus V, and then have a diode like this. You all agree that this is forward biased and current would flow in that direction. Everybody agree with that? Forward biased diode, at most, is going to have about 0.7 of a volt drop, and it'll let current just surge after that point. You all follow me? The actual equation is going to be E, and he has NV here, minus 1. Is that correct? And here, his value of N is 12. Now, do you remember how, in these problems, how this is usually done? They usually have V over they have over 26 millivolts. Do you remember this? 26 millivolt? How many do? If you take 1 over 26 millivolts, I haven't done that, but it should be around 12. That's what that A to N is. Can anybody do that? Or just do this, take 1 over 12, what do you get? You do that to me.
0.083 repeating.
All right, so this is a little higher value than all this. That's 83 millivolts. That's a threshold. I don't know if that's maybe a germanium nitride or something. It's a different compound, but for silicon, it's typically that value N is 1 over 26 millivolts, almost always. Anyway, for this one, he gave us 12, and then he gives you a value of voltage, right? And where does it go from?
0 to 2 uniformly distributed.
Okay, so what it means is this. You got F of the V of V to 1, and it's uniformly distributed, so this is going to have an area right here of 1/2. I mean, sorry, a height of 1/2. Do you all agree with that? If this is the voltage V and it's 2 volts, you all agree? If you look at this, and what's the first question you asked for?
That's or find the resulting mean value of current.
Okay, this is a great question. I've never asked this one, but I could see myself easily asking. So they want the expected value of the current, right? And first we need the what? F of V of the current. Do you all agree with that? So, or F of I. So F of I would be equal to F of V, right? And then it would be divided by simply di dv. I want to make sure that everybody sees what I'm doing. Do you all agree with that? The way I've got it is what? I know F of I di is equal to F of V dv, but now, right, I divide top and bottom by dv and I get di over dv. You all follow me? How many understand what I'm doing right? This should be obvious if you've done the work. So F of V is just a constant of 1/2. And then di dv, if this is I right here, I know I didn't give this to you for homework, but I think you can handle this level of problem. Di dv right here is going to be I naught right here, and it's going to be times N e to the V times N. And I might add that he has N equal 12 and I naught is equal to 10 to the minus 9 And so that's a realistic trickle current, by the way. That's a reverse trickle current. Do y'all remember these things? So this would be like the reverse bias current in a diode, which is about typically, if you get about a nanoamp, that's not a great diode, but it's pretty good. All right, so now I take the IUV and I put it there, and that's I naught right here. And it's going to be E to the eta or NV. And now I have to take V and put it in terms of I. Do you all agree with this part? I'm going to stop for 1 second. Catch up with me. I've just gone through the rigor of taking the F of V, which is just a half over the range V exists. And now I've taken that right there. We'll get the range I exists in a second. I've taken dV, or I mean dIdV, and I've put it there. Y'all with me? Just take a moment. Y'all agree with this? All right, now, what I need to do is find what I is, or what V is in terms of I, because that's what I need to plug in. And I'm going to bring it over here. So for this one, if you look here, for this thing, I take a look at that, and I get, really, it's going to be I is equal to I naught E to the NV right here, and then it's going to be minus I naught, and so I have to take I right here plus I naught is equal to I naught E to the NV. Are you with me? I'm just going through the example, right? Keep watching just for a second. Y'all follow me? The reasoning. Remember, I need V in terms of I. You'll notice I have E to the NV there. That's the key. So if I divide this by I naught, I have E to the NV, right? Take a moment. And what that does is make this pretty easy. Take a look at this. So that means this becomes 1/2 I naught, and then I can put I plus I naught over I naught. And you can see the I naught cancels, so I have basically 1/2 over I plus I naught is going to be my F of I. Do you all agree with that? Yes, sir.
Should it be multiplied by n, the denominator? Because
Oh, in the derivative, you're right. Hold on. This should have an N here. You're absolutely, and I do have an N there, but I didn't take it over here. So I'll put the N here and carry it through. So let's see. That means what happens. If I have an N here, I do have an N here as well, but you're right. An N is 12, and then that means this is going to be divided by N. Do you agree with that, class? I'm sorry, I don't mean to be sloppy. You with? Can you see it back there? Okay, now that's F of I. That's the density function, but we don't have the range. So what's the range going to be? Let me ask you this. Looking at this equation, when V is 0, what's the value of I?
0.
It's got to be 0, right? Because e to the 0 is 1, 1 minus 1. So I is going to range from 0, and what's the value? Here's a hint. Think about how the magnitude difference. What's the value of this when when V goes to 2 volts? I want you to see something. E to the 12 times 2 is e to the 24. E to the 24 minus 1 is about e to the 24. Do you agree with that? You go ahead and put in e to the 24 in your calculators. It's a significant number. He's doing it for me. Thank you. What do you get, CJ?
it's like 2.64 times 10 to the 10. It's pretty big.
In other words, it's too big to worry about. So this is about, if you take a look at this, this is about I naught e to the NV. Just leave it as that. You all with me, class? That's the upper limit. So now we can get the mean. You all agree? We have the density function for I, we have the limits of I, and we need the mean. So the expected value, this is a good problem, by the way, of I, and I can see this in a microelectronics. Have you had analog? Now, I'm not sure you would ask this exactly. Dr. Newman, have you had digital? All right, now, not in his digital, did he ask anything like this in his digital class?
We didn't have him for Digi.
Huh?
I said, I think a bunch of us didn't have him for Digi. I had, some of
Who'd
us
you
did.
have?
We had, just Sheeta.
Okay, well, Dr. Newman, who had Newman? Dr. Newman. Did he cover anything like this? He did? All right, he's very good about showing classic problem. This is a classic problem, by the way, this one. So here, expected value. Well, that means I'm going to integrate over the range from 0 to I naught, right? It's going to be 0 to I naught E, and it would be 2 times n or 24. Do you agree with that? That would be the upper limit. I'm ignoring the -1 business. Then I have to take I, right here, and then I have to take f of I. That right there. So it's going to be, I'll take the 1/2 out in front. That means I divide this by I plus I naught and n. Now, you see that n is 12, so I'll just make this divided by 24. And I want you to take a look at this, and I'm going to ask an obvious question. Y'all, everybody understand what I'm doing here? This is the mean. Okay, how would you do that? Don't worry about the value of I naught. How would you do it? What's the natural trick? You look at this, you'd like to have 1 over something, just something, like 1 over u or something. So make I, I'll erase this, and use this part of the board. For this part, we can do it by making u equals to I plus I naught, and that means du is equal to di, and then I can recast this as simply 1 over 24 integral, and here I've got simply u, and then I itself is going to be u minus I naught right here, and du is just di. You all see what I'm doing here? I'm trying to make it clear, right? Substitute. What are the limits though? When here I goes from 0, right, to I naught e to the 24th. Everybody agree with this? I'm not going to spend a whole lot of time on this. This u over u goes to 1. Then I have minus I naught over u here. You all with me on this one, class? So what I'm going to do is say this is going to be 1 over 24. First, u over u is 1. di integrated as I from 0 to this is just going to be I naught e to the 24. That's the upper range of the value. And then I have minus I naught, and I have di, I should say this would be du right here. Now it's d with the transformation. And I have the integral of 1 over u du, and that's the natural log, right, of the upper limit of I naught, and it would be e to the 24th. Are you with me on this? I'm making sure. You believe me? The reason I didn't put values in for this, I want you to see the cancellations. All right, now, in this one right here, this part, if you look at this, I have a natural log of this. So I have I naught, and then I have the natural log here. Wait a second. sorry, I did one thing wrong here. I forgot to do the substitution for the values. If u is equal to I plus I naught, when I is 0, the lower limit is I naught. And then the upper limit here would be I naught e to, basically is going to be, I mean, what really is I naught, and it's going to be e to the 24th, right there, plus 1. But e to the 24th plus 1 is about e to the 24th, so I didn't mess with that. And that would be the range, and then the I naughts would cancel right here. And I want to make sure you see this. So if I take the natural log of e to the 24th here, that's still going to be I naught right here, and it's going to be simply times 24. Y'all follow me? If you take the log of e to the a, it's just a. Log and e are basically reverse functions. If you take e to the a and take the log of it, you get a. Y'all follow me? Well, that is I naught. And that means, really what I have is 1, and I'll need this from you guys, 1 over 24, and I can take I naught out in front, but this term is insignificant. So it's going to be that times e to the 24th would be the mean value. Can you tell me what that is? I naught is 10 to the minus 9th, and this is going to be times e to the 24th over 24. And I did this one. 1.104, isn't that the answer?
Yes.
Or 1 point, yeah.
3.7.
Yeah, it's basically 1.104. And that's the way you do this problem. One question that I want to ask it, but when I do this, it's to give you a hint on what you might see on an exam. I do this a lot. If you look at my lectures, I'm always doing this. So that is the mean value, right? How would you get the mean squared value?
Just do I squared on top.
Well, now you got an I squared, right? And you'll notice one thing. It is still the key to make the substitution here to get the value. But that integration is doable as well. Do you all follow me? You would make u equals I plus I naught. du is the same thing. The limits change here, but it's a straightforward integration. It's really I to a power n, right? Integrated. That's not a hard integration. So those are interesting. Is there another part to that one?
No, just that.
Okay, one last thing I'm going to ask you. Since we have the density function, had the density function, which was really, it was of the form 1 over I plus I naught, right? If you want the probability of I greater than a certain value or less than a certain value, you would simply do the integration with the limits associated with what you want, the probability to be. And remember that value of I right there has a range, basically because the voltage is from 0 to 2, the value of I has a limit to it. It doesn't go to infinity. Just remember that, okay? All right. Now, next. That's a good problem. That's the reason I selected that. Next one I want to talk about, we did 2-8.2, didn't we?
Yes.
Okay. 2-8.1, briefly, I'm going to touch on that, and the reason is I don't think he brings this out in the text or in any of the reading, and I didn't look at Chan's book, but these are, quote, memory-less events, memory-less events. They don't remember anything, which is nice. So the time history has no bearing in this. I was going to do the Erlang distribution, but I'm not going to do it today because I don't have the time. Erlang is just if you have something that's got an exponential time to failure, and say with light bulbs, and you want the time to failure of an event where you have one light bulb, as soon as it fails, you replace it with another light bulb, and until it fails, and then when it fails, another light bulb till it fails. And they want the mean squared value, the time to failure, and the mean value to time to failure. That's called an Erlang distribution that we'll get some other time. It is important for a lot of things in the physical world. But 2.81, this is the problem. Can you tell me this, Elisha, please?
For the communication satellite system with problem 2-7.3, find the conditional probability that the satellite will survive for 10 years or more, given that it's survived for 5 years.
Yeah, so really, they're looking for a probability that this thing, T, goes on greater than 10 years, given that it has survived 5 years. Now, this is a probability, not a probability density function we're talking about. The thing about this is, if you think about the probability density function for this event, and I'll just say it's going to be f of t itself, given that t is greater than 5 years. So what I'm really saying, it made it to 5. What's the probability after that point? We can worry about after 10 in a second, but this is a general, what happens with that? Well, this is really going to be, if you think about it, it's 1 over the mean value, exp, and here it's going to be minus t over tau bar. And then it's the probability that it's going to be greater than 5, right? Or that's what he's saying. So we have to normalize to that area. Think about this. If you look at time and you look at this, f of, I'll call it t here, it does this. It says 1 over t bar. Can you all follow me on that? Now, anytime what we're talking about, if you pick any time, the probability that it fails somewhere between the beginning and that time is just the area under this curve. The probability it doesn't fail, or that area would be 1 minus e to the minus t over the mean time to failure, right? That means that the time, this time up here is really going to be simply e to the minus t over t prime. That would be the area left. Do y'all follow me on this one? So when you think about this, if you normalize with that area right there, it's just going to be divided by e to the minus, and this is the time, so this would be like 5 over 6, right? Just follow me on this one. So this is going to be equal to 1 over 6, and 6 years is the mean time, and then it's going to be exp to the minus t right here, but it's going to be minus 5, 6, or minus 5, pardon me, divided by 6. If you take this upstairs, it's going to be e to the plus 5, 6, right? Then you have e to the a, times e to the b, so you can add exponents, and you're going to get this, right? Now here's my whole point on this one. When you look at this difference, t minus 5, right there, is significant, because what it really says is this, that the probability that t is greater than 10 years, given that it lasted t greater than 5, is the same thing as the probability of t greater than 5 years. It's only has to do with the, if you say it lasted to 5 years, you'd have to normalize the density function. It lasted 5 years. What's the probability it's going to fail at 10 years or greater? It would be the same thing if you start at 0 and it gets over 5 years. Y'all with me? It's called a memory list system. Anytime you're given that the event's going to last this long with an exponential distribution, the only thing you worry about is the time difference between how far it lasts and what they want to know about. Does it fail before or after some other point in time greater than that? With me? How many understand that? It's not a hard concept, but you need to at least apply it to a few problems to really get a handle on it. That's 8.1. I wanted to do that. We did 8.2. I think I wanted to do one other one before I jump into the next section. Did we do 2-7.1, right? We did that one. Yeah, we did that. And this is, I think it's problem 2-8.3. Is that the one with the laser?
Yes.
All right, I want to do that one because it's got a Rayleigh distribution, and these are important. That might have a wrong answer too, I'm not sure. I was going to do the problem on radar 2-9.2, but I may not have time. I may have to go into that. So for this problem, it's going to be 2-8.3. How many tried this one? It's not meant to be a hard problem, but this is perfect in terms of using rails. So can you just briefly tell me what this says?
Laser weapon is fired many times at a circular target that is 1 meter in diameter, and it's found that 1/10 of the shots miss the target entirely.
So basically, 1/10 of the shots miss. All right. Now from that alone, we can get the information we need. Now remember, this is a Rayleigh distribution. I'm just trying to say 1/10 off the target. If A is a half meter, 1/10 or greater than a half meter away. That's the only thing I'm saying. So if you think about this, the Rayleigh distribution, and here I'm just talking about, this is going to be a measurement from the center of that target to a point of impact. And it would be, we're talking about something that's not a function of angle either. So this is going to be R over sigma squared, and that sigma would have to do with the Gaussian variation in x and y. EXP, and here it's going to be to the minus R squared over 2 sigma squared, R greater than 0 or equal to 0, and it goes on to infinity. And then from that you get the cumulative distribution function that the event is between 0 and R. When you integrate this thing and you end up getting 1 minus EXP to the minus R squared over 2 sigma squared. That's the probability that the event is less than R, right? And then the probability, really probability of the event or of a strike being greater than a half meter, I'll put it this way, or greater than some R, is going to be simply EXP to the minus R squared over 2 sigma squared. And the only thing I'm going to do is take that and subtract it from 1. You're left with this. So that's all well and good. What we need is that sigma squared information. We got to find that. So he says the probability that it's greater than a half meter, basically it's off the target, is 0.1, right? So you put 1 over 10, 10% don't hit, and that's equal to EXP to the minus, in this case, now you have to put the limits here, and that's going to be 1/2 meter squared over 2 sigma squared. What I want is sigma on this one. How many tried this problem? Didn't most of you do this? If you take a look at this, take the natural log of 0.1, and that's equal to, in this case, minus 1/8 divided by sigma squared. The only thing I did is take the log of both sides, because I need that. Y'all follow me? I had to take the log of both sides of this equation to get to that point. And then I can say that means sigma squared is equal to minus 1/8 natural log of 0.1. And can you tell me what that is? Or sigma, either one. There's a minus sign here above it. Anyone? Pardon me? 0.233, and that would be sigma squared? Or sigma?
That's sigma.
Sigma.
Okay, so that's sigma. All right. And if that's sigma, he wants information what's the probability that the strike is from 0 to, is it 1/10 of a meter or 1? Is it 1/10?
Yes.
Okay, so now he wants the probability that the strike is between 0 and 1/10, and that's the cumulative distribution function here, right? Does everybody understand what I'm doing? I'm going to use this one because now we got sigma, and we want to find the area under the curve from 0 to 1/10 of a meter, so R there is 1/10. Do you agree with that? All right, so this is going to be simply 1 minus EXP, and now I have minus 1 over 10 squared over 2 sigma squared, or 2 times, I'm just going to leave it as sigma squared. You got it that. And what is that value? I don't know what that is. I know I did this one. I don't remember. Does everybody understand what I'm doing? I know I'm going a little quick, but I'm assuming you've spent time with this. It's a good problem, by the way.
Yep. 0.088.
You have the solutions manual, is that what it is? 2-8.3. That's right, I don't remember.
That's what I got.
Part A.
There he's got 0.097.
For 2-8.3? Maybe I'm wrong. We got sigma, right? They got the wrong thing. They're using conditional probability where they shouldn't. That's my answer, but I got that right. The first part has no conditional probability. It says 10% of the arrows miss the target, right? Or 10% of the shots, right? 10% of the shots has nothing with conditional for given that anything. So that answer's wrong. That should be that value, or 0.088. You got a pen or pencil? Can you put 0.088 there? That's wrong in solutions. There's no conditional probability in the first one based on that, right? It doesn't say given that. It just says 8 to 10% miss. So if 10% miss, that would be the correct value for sigma. Then what's the next part? I think that's
For those shots that miss the target completely, the conditional probability that they come within 0.3 meters of the edge of the target.
okay, now this is a little different. the shots miss the target completely. So there's only 10% of the shots that miss the target completely with me. Now he wants the probability, if they miss, that they're within, let me just do it this way, right here. Now he says the probability, right here, of the strike point being greater than 1/2, less than, it would be 0.5 plus, is it 0.3 meters, right?
Yes.
All right, so this is gonna be 0.8 meters, and it says, but it's given that they miss, right? So now you take a look at this. This one has to be here. The probability that they miss is 10%. You know that, correct, class? I mean, we could put that we could calculate the probability, but it's already given, right? Probability that they miss, and now up here, the only thing you're gonna do is take the original density function, or the original, yeah, I can do it this way. Let's go ahead and get the density function, f of r given m. So this is gonna be the original, which is gonna be it's gonna be r right here divided by sigma squared exp to the minus r squared over 2 sigma squared. This is the original density function, is what I'm writing here. You all follow me on this, class? And then I have to divide that by the probability of that event occurring, which is 1/10 by specifying. He gave it. So this becomes 10 r over sigma squared, and then it's times exp to the minus r squared over 2 sigma squared. And the only thing I've done here is just take the 10 upstairs, right? Now he wants the probability density that it's with between, the strike is between 0.5 and 0.8 meters. And that's where we come over here to do this. Since we have the probability density function right here, we can go ahead and say that the probability that the strike is greater than 0.5 and less than 0.8 is going to be that density function. I'm going to take the 10 out in front. That density function, and then we integrate r over sigma squared exp to the minus r squared over 2 sigma squared dr, and this would go from 0.5 to 0.8. And if you think about this, when you do this integration, you're going to get 1 minus, or basically, I'm sorry, if you do this integration correctly, you end up with 10, and then you're going to get e to the minus, and this will be lower limit, which is going to be 0.5 squared over 2 sigma squared minus, and the upper limit is going to be exp to the minus 0.8 squared over 2 sigma squared. So could you do that for me? This will be right. Does everybody follow me? There's a 2 sigma squared over under both of those. Now I did this one. I thought the answer I got agreed with the book on this part, where the solution's made. Remember, sigma is, I guess I erased it. Sigma was equal to 0.232 or 322? 0.233. So that's e to the minus 0.5 squared, 2 sigma squared minus, I just want to finish this. I didn't get my problem in. I don't think there's 2 solution manuals for this. years, did you? I know it's a pain in the butt calculation. I did this one last night on MathCAD. I believe I got the answer, the solution, man. That first part is wrong.
Seems, I don't know if it's right, but it says, I got 0.97.
That's right.
0.097 or 97?
0.9725.
Yeah, exactly.
Yeah, that's correct, but the first answer is wrong. And it's, the one I put up is correct. Y'all with me, class? All right. I don't have enough time to get to the next part. So do me a favor. Let's go this row. So you just move, you can move right here. And then we're gonna open that row up. And